Okay, so I'm about to talk about how to solve these types of equations when they have a repeated root. But first, as a reminder, I've shown a couple different ways so far, I think 2 or 3 different ways for solving this type of equation. And in every way I've shown so far, and in every way to solve this equation that I'm aware of, at some point or other you're either going to come across this characteristic equation or you're going to come across this generating function. And in the cases where we deal with the characteristic equation, there's a condition that you can only you can only solve this thing, or so far I've only shown how to solve this thing, when the characteristic equation doesn't have a repeated root. And when we dealt with the generating function, it was a similar case. It was just that the denominator of the generating function couldn't have a repeated root. And so before I show how to deal with that special case, I just want to point out that those two cases are one and the same. You'll notice that with the characteristic equation, the coefficients go a, b, c as the power descends, and with the generating function, they're reverse, c, b, a. But as you can see in the second order case, if you set the denominator of the generating function equal to 0, you use the quadratic formula and you get this, and with the characteristic equation you get this. So they're only slightly different. The denominator here has 2c, over here it has 2a. But the important thing is the discriminant, the part under the root here, and you'll notice that in both cases it's exactly the same. Here I wrote 4ca just to point out that in this case the first coefficient is c and the last one's a. But they're the same thing, and the important thing about that is that when the discriminant is equal to 0, that's when you have a repeated root, because you're doing plus or minus 0, so you get a multiplicity there. But then the question comes up, what about higher order recurrence relations of these linear, really long name recurrence relations? Because I want all of these techniques that I'm showing to apply for higher order things, and if you're dealing with a third or fourth or fifth order, well, there is a cubic equation, but the equations kind of run out, I think, at about order 5. It's either 5 or 6. There's no equation to solve for the roots. And so can we still say that these two cases are the same when the generating function has a repeated root in the denominator, and when the characteristic equation has a repeated root? And so let's just look at a fourth order equation. This would be the generating function. You get it in the exact same way, and this would be the characteristic equation that you also get in the exact same way. If you're wondering where I got those from, just watch the earlier videos, and you'll see how it's really easy to apply that for higher order. So what we want to do here is show the denominator of this characteristic equation here, of the generating function here. We want to show that this has repeated roots in the same cases where this has repeated roots. And so let's just take the denominator of this equation here. So we take the denominator of the generating function and we set it equal to 0. Then you just use a substitution, x is equal to 1 over lambda, plug them in, multiply both sides by lambda cubed, and then you arrive at this equation, which is exactly the characteristic equation. And so clearly these would have repeated roots. What that means is that this has a repeated root if and only if this has a repeated root. And so you can see how this method doesn't use like the quadratic formula or anything like that, and so it could be generalized for higher powers. So in the next video I'm going to show how you actually do solve one of these repeated root cases, now that we know that there's only one case we have to deal with, the one repeated root case.